Welcome once again to our online classes, and today we are going to study reactions and mechanisms of alkynes. One of the reactions that alkynes can undergo is hydrohalogenation. This is the addition of hydrogen halide to a carbon-carbon triple bond, and this halogen can either be chloride or bromide, as we're going to see. Addition of 1 mole of hydrogen halide can lead to the formation of what we call a vinyl halide. A vinyl halide, one halogen atom is bonded to one carbon of the carbon-carbon double bond. If it happens that we add another 1 mole of hydrogen halide, we are now going to form an alkene, and this time we are forming a geminal halide. A geminal halide, the two halogen atoms are bonded to the same carbon. This type of reactions is Markovnikov. It means that hydrogen atom is going to be bonded to the least substituted carbon, while halogen atom will be bonded to the most substituted carbon. Let's look at an example. If you have carbon triple bond, and we have CH3, and we have H, and we have Cl. So we have HCl. We know that chloride atoms is more electronegative than hydrogen, and therefore this bond will cleave heterolytically, leading to the electrophilic attack of the pi bond. And this is going to give a carbocation on this carbon here, what we call a vinyl carbocation. So this is what we are going to form. We are going to have carbon-carbon double bond, but then we have a carbocation on this carbon. We still have our CH3. We have our hydrogen, the newly formed hydrogen, and the hydrogen that we had initially. And remember, when this chloride atom cleaved heterolytically, it had 2 electrons extra. This is what we call a vinyl carbocation. So this carbon here is having 6 electrons, and therefore 1, 2, 3, 4, 5, 6. So because it's having 6 electrons, it is unstable, and it acts now like electrophile. This nucleophile chloride atom will then donate electrons, leading to what we call the nucleophile attack of the carbocation, or the vinyl carbocation, which is going to give us a carbon-carbon double bond. And this time round we are forming a chloride atom, new bond, and we then have our CH3, and we have our H, and the H was formed, and this is what we call a vinyl halide. The same process is still going to take place to our vinyl halide, and let's take a look. So we have our hydrogen, carbon, hydrogen, and this is a double bond, carbon. We have our chloride atom, and we have our CH3. The same process takes place again. We have H bonded to chloride atom, heterolytical cleavage of the bond, and the electrophilic attack of the pi bond, and this is going to give us carbon and a carbocation on this carbon. Once again, we already have our chloride atom that we formed initially, and we have our CH3 bond, and we have our hydrogen, and we have our second hydrogen we formed, and we have the third hydrogen that we have just formed in the previous reaction. And with this carbocation, remember, when this chloride atom cleaved, it cleaved heterolytically, and it came with 2 extra atoms. The same thing, this carbocation carbon has it has 6 electrons, so it is electrophile. What does that mean? We are going to have a nucleophile attack of this carbocation to give us what we call carbon-carbon, chloride atom, CH3, hydrogen, And this is what we call a geminal halide. Now let's take a look. Initially we formed vinyl halide, and we add another 1 mole, the one that we have just added here, to give us a geminal halide. Let's look at the chloride atoms. They are formed on the carbon, which is mostly substituted. This carbon is substituted to this methyl group, making it the most substituted carbon of these two carbons. And therefore, you can see it follows Markovnikov rules. Markovnikov rules. So this is how hydrohalogenation reaction takes place. The second type of reaction is halogenation, and this is the addition of halogens to alkynes in this scenario. And whenever this takes place, we are going to form, in each step it occurs, we are going to form a bridge halonium ion, which is unstable. And let's take a look. So we have carbon-carbon triple bond. Let's say we have our CH3 and we have our H. And in halogenation, the first step, or just by adding 1 mole of halogen, let's say this halogen can be chloride, it can be bromine, so we have Cl2 and Br2. Now, the first step is going to give us what we call trans halide, dihalide, and then the next step, another addition of halogen or another halogenation process, is going to give us tetrahalide. Now, the first step, meaning that the two halogen atoms are opposite each other, so we are going to, let's say we're adding chloride. Okay, I'll just put these two, and this bond is going to break, and when it breaks, we are going to have electrophilic attack of the pi bond, and we are going to form bridge halonium ion. So it means that this one is going to come to this carbon. This is going to give us what we call a bridge. So this is our chlorine, and our chlorine had lost 2 electrons, and we have our hydrogen, and we have our CH3, and this chlorine here, chloride atom here, is what we have down here. What happens next is that this bond will break and donate those 2 electrons to this chloride atom, making this chloride atom or the nucleophile attack of the pi bond, and that's going to give us a new structure, or it's going to give us trans halide, which looks like this. So we have carbon double bond, we have our hydrogen, we have our chloride and on this carbon we have this chloride atom formed here, and we have our CH3. So you can see we have formed our trans halide. So let's perform another halogenation and see what's going to take place. Let's draw our structure. So we have chloride, we have CH3, we have chloride atom, and we have our H. The same process repeats itself. Another heterolytic cleavage. We still have these our 2 electrons, electrophilic attack. We still have the same happening, giving us this carbon single bond, and you have our chloride atom bridge. Okay, we have our H already, we have our chloride atom, and we have our chloride atom and CH3. And what happens next? We have our chloride atom, which was cleaved here, this one, which is now our nucleophile, and this bond will break, and this Cl, this carbon bond will remain the same. it will remain intact, and when it breaks, it means that there will be a nucleophile attack of this carbon, giving us a final structure of carbon single bond, and we have our chloride atom, we have our CH3, and on this carbon we add the initially chloride atom, and now the newly formed chloride atom and H, which was there initially. So this is what we call a tetrahalide. So this is how halogenation of alkynes take place. The first thing is the cleavage leading to the formation of the bridged halonium ion, also here still bridged halonium ion, and then the nucleophilic attack of the carbon leading to formation of tetrahalide. So you must be very careful when you're following this type of reactions, because you need to understand, do you add 1 moles or 2 equivalents, meaning that 2 moles. So if you are adding only 1 mole, meaning you are going to form trans halide, but if you are adding 2 moles, you are going to have tetrahalide. So let's look at hydration of alkynes, and this is the addition of water to form ketones. And when we add water, we know that from our previous classes that water is a weak acid, and therefore it cannot protonate the pi bond, and we are going to need a strong acids which are going to activate the pi bond. And hydration of alkynes take place in the presence of strong acid like sulfuric acid and in the presence of mercury as a catalyst. When this happens, you are going to form an enol, and enol is not stable, and stabilization of this enol can lead to the formation of a ketone. For example, if you have C double bond C, let's say our R2 and our R1, okay, and then we add water in the presence of mercury, and mercury, okay, we are going to have enol. So we're going to have our C, but we're going to have our enol, and we're going to have our R2 this side, and we have our R1, and we have our H. So this is what we call the enol. So this enol is not stable, and therefore tautomerization of the enol to form a ketoform, and this is going to give us a ketone, meaning we're going to have carbon and our R2, and this carbon H and our R1. So this is the ketone which is formed. So let's look a real example. The first thing is the addition of the electrophile to the pi bond. So let's look at a reaction which takes place. So we have carbon-carbon double bond CH3, and we have CH3, and the first thing I've said, it is the electrophilic attack of the pi bond. So we have our acid, which is the hydronium, and this bond will be broken, leading to the electrophilic attack of the pi bond to give us a vinyl carbocation. So we're going to have vinyl carbocation formed, and we have our CH3, and the newly formed hydrogen atom plus water. And what will happen next is the nucleophilic attack of the vinyl carbocation. So the nucleophilic attack of the vinyl carbocation. So this is the vinyl carbocation, and the nucleophilic attack means that this one will come and we're gonna form carbon double bond, oxygen bonded to how many electrons? And this is our 1, 2, and we have our CH3, and we have our CH3, and we have our H. Now with this nucleophilic attack of water. So let's redraw it here. We have CC. So we have our CH3, we have our CH3, and we have hydrogen. So this one will be followed by the loss of the proton to form enol. So first, remember we had nucleophilic attack of water to the vinyl carbocation to give us this product here, and followed by the loss of one of the protons here so that we can form an enol. So we're gonna have a loss of proton, or what we call deprotonation. So you're going to have a loss of this proton, and when that occurs, we are going to form. So with that, you can form enol. So you have C, then you have O with one hydrogen, and then you have initial electrons which were there, and the new electrons which have been formed. And here we still have our hydrogen, we still have our CH3, and we still have our CH3, and this is what we call the enol. This is what we call the enol. Formed our acid back, and once we formed our acid, so we are going to have a loss of protons. So once we have our acid, we are going to have protonation of this double bond, or protonation of this double bond. So we can do protonation of the double bond. Now what we in the process of, so we have O, and 1, 2, and we have CH3, we have H, and we have CH3. So we're going to have protonation of this carbon double bond to form a carbocation. So we're going to have protonation. We are going to protonate this pi bond, H2 plus the space, okay, and that's going to give us this one here. So we're going to have C, but now we have a carbocation because of the pi bond, and we have this bond, newly formed bond, the originally bond that we had, and the CH3, and now we have still in contact. We have 1, 2, 3, 4. So now actually there's a structure formed, or a resonance tabular structure, that's what we call it. And if you look, this carbon here is having less electrons, it is electrophile, and there are some electrons here which can come to fill this so that it becomes stable, and then this is what happens. So this one is going to give us carbon, a double bond with hydrogen and our 2 electrons still, and this is, we have our hydrogen, CH3, we have CH3, we have hydrogen. Hey, there's no space, but then you still have our CH3. And then the final step to get our ketone is to do deprotonation of this hydrogen here. This hydrogen here, we're going to deprotonate it or to remove it so that we can have our ketone. And remember, this was a plus when it lost here, so we're going to have our hydrogen being deprotonated, so this bond will be broken to fill these 2 electrons, and then this hydrogen will be removed, leading to the formation of carbon. This is a double bond, and this is our CH3, and this is our CH3, and this is our hydrogen, and this is our hydrogen, and from this is what we call the ketone. So this is how a ketone is formed. The first step is the electrophilic attack of the pi bond, and the second step, that's going to give us vinyl carbocation, followed by the nucleophilic attack of water to give us the enol, and then nucleophilic attack of the enol to give us a carbocation. Hydroboration oxidation is the addition of borane followed by oxidation to form a carbonyl compound, for example, and this carbonyl compound can be either aldehyde, or it can either be a ketone, depending on which type of alkyne are you dealing with. Is it internal or a terminal alkyne, as we are going to see in the example. So the first thing we need to do is to do hydroboration to form organoborane. So let's say we have our R1 bonded to carbon-carbon triple bond, and this is our R2, and we would perform what we call hydroboration, which is going to give us what we call organoborane BH2 R2H, and we have our R1. So this is what we call organoborane. Now, after this, we can perform our oxidation. So we have seen how do we perform our oxidation, OH, and then carbon, OH. This is R2, R1, and this is H, and this is enol. So let me just draw our enol here properly, because there's something I would like to show here. So we have our R2, our R1, and our H. So this means that this reaction is forward and reverse, but forward reaction is favored because this enol is unstable, and tautomerization will occur so that we can have our, in this case, because of this R2, we are going to have our ketone R2, R1, and H. So in this case, we can have our ketone. And let's look some examples that can give us aldehyde and ketone. So if we're dealing with a terminal alkyne and you do hydroboration, oxidation reaction, you are going to have an aldehyde. This is going to give you an aldehyde. So you're going to have a carbon, so that one I'll just call it R and H. So if you have a terminal, this is a terminal alkyne, you're going to form an aldehyde. And if it happens that you have internal, then you do hydroboration followed by oxidation, then you are going to have a ketone. This is a carbon, and then that one. Okay, so this is H, and that. So you can form a ketone. So if you are given, let's say you are given a question and you are told to give the products of the following, you can be tested the same type of reagents, and you can be tested to know if you understand if you are working with the terminal or internal. This is internal. So you must be able to understand the product that you are going to have. It can either be aldehyde or a ketone when you are dealing with alkynes. So if it is a terminal alkyne and you perform hydroboration oxidation, you are going to have an aldehyde. And if you are working with internal alkyne and you are performing the same hydroboration oxidation, you are going to have a ketone. So you must be able to understand which type of an alkyne are you working with.